So in this video, we're going to look at question B of question 4 in 2023 paper. So it says the Iridium satellite telephone system uses a constellation of 66 satellites orbiting at an altitude of 780 kilometers above the surface of the Earth. The first part wanted to calculate the horizontal radius of the area covered by any one satellite. This is the radius of the flat circle within the horizon, i.e. the radius of one of the small circles illustrated in figure 11. So we want to calculate the radius of I suppose a horizontal circle that one of the satellites. Okay, so I think we can do something like this. Let me draw the diagram first. So this is the Earth, and then we have a satellite over here. So for the satellite, what's given is the height. We know the height. And then we know the height. And the area covered should be like this. A tangent to either side. And then if this is the center of a circle, we know that these two are the radius. So let's say this is R, and this should be right angles. And what we want to calculate is this. We want to calculate this radius. So, okay, how do we calculate this? Well, we also know that this length is R. I think we need to establish some kind of relation over here. So I don't think we can utilize any of the triangles in this case, because for R, yeah, okay, so let me see if we can utilize any of the angles. So let's say this is theta, then this angle is 90 minus theta, and then this angle is theta. So I think we can utilize triangle in this case. Well, I think we can utilize a bit of trigonometry. So we have sine of theta. We can get the sine of theta utilizing this triangle. Right, so this, we have R over R. And then utilizing this triangle, we can get, this is a right angle, so we can get the cosine of theta. So we have the cosine of theta is equal to, this should be R over, this is R plus H. So right now in this equation, all what we have is just theta as a variable. And then we can, to eliminate the angles and such, we can say sine of theta squared plus cosine of theta squared is equal to 1. So we have r squared over r squared plus, this is r squared over r plus h squared is equal to 1. And then we can simply solve for r. We can multiply both sides by r squared, multiply by r plus h squared. So we get r squared, and this is r plus h squared plus, this should be r to the power of 4, is equal to r squared r plus h squared. And then we get r squared is equal to this minus that, so we can factor out an r squared, and inside we should have r plus h squared plus, should be minus r squared over r plus h squared. And yeah, so I can break this down to 2. So we should have r squared. And then this is minus r to the power 4 over r plus h squared. And we still have a square root, so we should have, we can factor out an r, so we have r, and then we have 1 minus r squared over r plus h squared. And then what we have to do simply is to quantify this. So we plug in the values, and we should have r over here. That should be the radius of the Earth, which is 6.37 10 to the 6 multiplied by the square root of this is 1 minus 6.37 power of 6 squared over, this is 37 to the power of 6 plus the height. The height is given as 780 10 to the 3 squared. So we have this, that is 2 point, let's say 89 times 10 to the 6 meters. Yeah, okay, now this should be answer to the first part of the question. Now let's see the second part. So the second part asks, in practice, the effective radius is approximately 2350 kilometers. The power distributed by the satellite transmitted to this area is about 200 watts. Calculate the intensity of the signal at the Earth's surface. Okay, this is really simple, so we can just get intensity is power over area, right? The power is 200 watts, and the area radius, it only gave us the horizontal radius. So assuming, because there's 66 satellites, so we can assume that the surface covered by each satellite is approximately flat. So we can just use pi r squared. Pi times, it's 2350, right? Yeah, okay. 2350 times 10 to the 3 squared, pi r squared. And we should have, that is 200 over pi times 2350 10 to the 3 squared. Now that is approximately 1.15 times 10 to the minus 11 watts meter minus 2. And then let's see the third part. The third part over here says the movement of a satellite relative to the Earth's surface introduces the Doppler effect. If the wavelength of the signal from the satellite is lambda, the speed of the satellite v and the speed of light c produce an expression for the shifted wavelength lambda prime observed by the receiver as the satellite recedes. Okay, so simply just use the Doppler effect to assess this situation. Well, first of all, we need to base our calculations around v is equal to f lambda. So first of all, okay, so initially we have c is equal to f lambda. So f is c over lambda. We might use this later. And then for the new equation, we should have, it says it's receding, right? As the satellite recedes. So the new speed should be c plus v. Plus v, the speed of the satellite, is equal to frequency multiplied lambda prime. So the lambda prime should be equal to this divided by frequency, which is over here. That should be lambda over c multiplied by c plus v. And then, so lambda prime should be equal to lambda multiplied by 1 plus v over c. And that should be the answer to the third part. This is the answer to the second part. And let's see the next part. The next part says, using a suitable approximation, provide an expression for the apparent shift in frequency. Well, this is also based on the Doppler effect, right? So, yeah. So, an approximation. Well, in this case, we can assume that the wavelength is unchanged. So we have something like this. We have v is equal to f lambda, right? And then if a lambda remains constant, what we should have over here is lambda is equal to c over f. And yeah, okay. Let me see. Yeah, okay. And then the new one should be c plus v. C plus v is equal to f prime lambda. So f prime should be equal to f over c multiplied by c plus v. So we have f1 plus v over c. So therefore the fractional change, I suppose, is just this. We have f prime minus f over f. So we should have f multiplied by v over c over f, and we get v over c as the fractional change. So this should be the answer to the question. Now let's see the last part. So the last part over here says, now consider the satellite moving above the receiver on the Earth's surface. For the effective radius of coverage in the second part says, so that's just 2350 kilometers. Calculate f minimum and f maximum as observed, given the transmission frequency of 1620 megahertz, and thus state the bandwidth that must be set aside to manage the Doppler shift. Okay, so I suppose we can apply the fractional change of frequency as well in this case. And so the only thing that we need is the speed of recession in this case. Now we can return to this diagram over here. Well, what we have is that the satellite is orbiting around Earth, so at this very instance it should be traveling in this direction. We're assuming that it's traveling in that direction. And then, let's see, utilizing the angles over here. We have, this is theta, so this is 90 degrees minus theta, and then this should be theta as well. So we can calculate the speed for recession in this case. And then before that, it didn't mention anything about the speed of the satellite, so we have to calculate that ourselves. And then we can just multiply that by cosine theta to get the speed of recession, and then calculate the fractional change of frequency. Okay, so first of all, we need this. We need v squared over r is equal to gm over r squared. So we have v should be equal to gm over r, and that in this case is, wait, this is gm over, this is r plus h, yeah. Because it's orbiting at a height of 780 kilometers above the surface of the Earth. So we should have square root, and then we have g, which is it given over here? No, okay, so let's just say 6.67 10 to the minus 11 multiplied by, this is mass of the Earth, which is 5.97 10 to the 24 over r 6.37 10 to the 6 plus 780 10 to the 3. Yeah, okay, so we have over here we have 7462.72 meters per second. And utilizing this, we can get the fractional change in frequency. So the fractional change in frequency is just 6462.72 divided by 3 times 10 to the power of 8, and we get, that is 2.49 times 10 to the minus 5. And the bandwidth is simply the shift in frequency, I suppose. So we have we should have let's say b should be equal to 2.49 times 10 to the minus 5 multiplied by the initial frequency. The initial frequency is given over here, 1620 megahertz times 10 to the 6. Now that is equal to, it's a fractional change, so there is recession, and then the satellite can also approach. So suppose this fractional change multiplied by 2. Yeah, for the bandwidth. And so we have this multiplied by 10 to the 6, and then multiplied by 2. So we get 80597.38 hertz, and this should be the answer to the question.